Okay. So, concept maps. This is something that we haven't talked about yet. I said I'd get to it as we continue. And that's because we really hadn't covered very much yet, and so it wouldn't have made sense if I tried explaining it at the beginning. But we're going to take 5 minutes now and really think about this. So for this assignment, it's relatively challenging, and so you can do it by yourself if you'd like, but you also could do it in groups of up to 3. And the aim of this is to make sure that you're seeing the Earth as a connected system. This is a different class from, say, if you just take the atmosphere, if you just take oceanography. This is really all about stressing the links between these different spheres. And sometimes that can get a bit lost when we're studying something in detail. And so this is to help you link together the big ideas and put together sort of the big picture. So it's due before the final because I think it's a really helpful sort of studying tool. As you go through your notes and you're putting all of this information together, it should really help before the final. So I wanted to give you a quick example of what on earth I mean by a concept map, because there's lots of different definitions out there. So this is, hopefully everyone can read this. My writing is really not very good. So this is how I would start. I have my 4 different spheres on here. My geosphere, atmosphere, biosphere, and hydrosphere. If you wanted to, you could look at the anthroposphere as well. But these are the big 4 that I'd like you to include. And then what I want you to do is think about either subdividing those spheres down a little bit. So for example, for atmosphere, I might talk about atmospheric composition, atmospheric sort of structure, atmospheric circulation, the movement. So for example, I might start subdividing this down into composition, structure, and I said circulation, so the movement of the atmosphere. And then you want to, so you can do that with the different spheres. So the hydrosphere you might separate into oceans versus freshwater versus sort of frozen, okay? And we'll come on to that. But then I want you to think about what links together those different things. So why did we say that volcanoes were important for the Earth system? Can anyone remember one of the things we said? Yeah?
They gave us like stronger greenhouse effect early in the Earth's history.
Absolutely. In fact, volcanoes created our atmosphere. We're going to do that today. And so that's one of the easiest things. We can say the geosphere, volcanoes created the atmosphere, okay? And you can put, we've got CO2 and H2O, and we'll go into that today, things like that. What else do volcanoes create that we like to live on? Yeah. Land, absolutely. Volcanoes create new areas of land, and that's probably pretty important for the biosphere. So we can say volcanoes create land. Okay, what else do they put into the atmosphere, perhaps, other than gases? Yeah. Energy? Yeah, absolutely. They're important in sort of providing energy for the system. And energy is a difficult one to track through these sort of maps, but you can definitely talk about energy. What else do they put into, oh, actually, I have one last thing to add, which is, as well as creating land, which allows sort of the biosphere to exist, whenever we create land or whenever we have plate tectonics and mountains built and things like that, then we're also going to be affecting how the atmosphere moves. So you can also have an arrow going to circulation saying, so, sort of convergent boundaries, creating mountains. I'm not going to write all of it right now, but you get the idea, okay? So this is a challenge. I have a little piece of paper. Most of the ones I got given last year, like on this size piece of paper, because it rapidly gets really complicated. But that means that you're really putting together a lot of these ideas, and you can subdivide more than I've done, and that might help you come up with the links. But as we go through the class, I want you to start thinking about these things. Think about how the fact that we have plate tectonic activity and movement of the geosphere has affected things like life on Earth, things like the composition, the structure, the circulation of the atmosphere, the fact that we have H2O, water vapor, coming out of the volcanoes has created our oceans. The fact that we have plate tectonic divergent boundaries has created our ocean basins. So all of these links I'd like you to start thinking about, okay? So that's a rough idea of what I'm after. And there's a grading rubric online as well. And so if you have questions, then your TAs, I'm sure, would be very happy to answer questions. I would be happy to answer questions. And I have some examples from last year in my office, so if you have further thoughts, come find me. Does anyone want to ask anything right now? It may take a few drafts to get it, because there's a lot of information. Okay. So this is where we didn't quite get to on Wednesday, as we ran out of time a little towards the end. So we talked on Wednesday about the rock cycle, how we go from magma to form igneous rock, which weathers away along with metamorphic and sedimentary rock. And then we can take the sediment that results from that physical weathering, the chemical weathering, and we can compact it and cement it together to form sedimentary rocks. And if we heat up igneous or sedimentary rocks, we get metamorphic rocks. So we have this cycle going on that's constantly moving around the rock material at Earth's surface. And then we talked about how we could try and start constructing like a time scale for Earth. And we talked about two types of dating. We talked about relative dating, which means that we take, say, a sort of cross-section through the Earth's crust, sort of a geological cross-section of the different rock beds, and we see if we can come up with the story of how that came about. So if we can tell the story through time of how we've ended up with this sort of nice sort of image cross-section. But that only gives us a relative timescale. That doesn't give us absolute dates, and that's what we're interested in as well. And so I wanted to talk about absolute time, absolute dating. And the way that we get at absolute time is by using radioactive decay. So most people have heard of carbon dating, and that's something that we can do here at UCI. It's some of what my research is on, where we can take something that was living, anything that contains carbon that sort of grew in the last 40, 50,000 years, and we can sort of time its decay, or we can work out how old it was, or when it sort of grew, or when it lived, by looking at how much of that carbon is left. And so our radioactive decay is predictable. It follows certain physical laws that means it doesn't necessarily change due to increased temperature or pressure or anything like that. It's predictable. And so we care about two things. First of all, the amount of radioactive material there to begin with, because if there isn't very much there, it's going to be really difficult for us to measure it. And then the second thing we care about is the half-life. So for carbon, what I was talking about, it has a much shorter half-life of just a few thousand years. And so if we want to use it to date the formation of the Earth, then it's going to be pretty useless for us. But if we have something with a much longer half-life, then that will make more sense. And I wanted to talk a little bit more about this concept of half-life related to these questions that I posted in the lecture on Wednesday. So let's look at my somewhat dodgily drawn graph again. Okay, so I have a little graph here. I have percentage of our radioactive element on the y-axis, and then I have number of half-lives that have occurred in the x-axis there. So when that rock initially forms, it's going to have 100% of that radioactive element in it, okay? So at time 0, we're going to have 100%. So we can put a point up here. After one half-life has sort of elapsed, so after our million years, after our few thousand years, after one half-life has gone past, then we're going to have half of what we had originally, okay? So after one half-life, we have 50%. How much of my original radioactive element am I going to have left after two half-lives? 25%. So we're taking that 50% and we're halving it again. So at 2, I'm going to have 25%. What am I going to have after 3? 12.5%, because we're taking that 25 and dividing. So it's sort of somewhere down here-ish. What am I going to have next? 6.25, okay, and 3. And so this is what our exponential decay is. It's this nice sort of line that comes down here, and it never quite reaches 0, but it gets very, very, very close. Okay, and that's called exponential decay. Okay, the rate at which it drops off is dependent on how much there is to begin with. Okay, and now you can see how if we have one half-life at sort of a few thousand years, we have lots left, we can date it easily. As we get further and further along, it becomes much more difficult to date. Everyone's following so far? Okay. So if I start off with 100 radioactive atoms, how many am I going to end up with after 2 half-lives? 25. What happens if I start off with 1,000,000 atoms to begin with? How many am I going to be left with after 2 half-lives? Yeah, 250,000? What do you think is going to be easier for me to measure? 25 or 250,000? 250,000, absolutely. It's going to be easier for me to measure that. And so that's why the amount of that radioactive material that you have to begin with makes a difference. So it's easier for us to measure when there's more of it. Okay, so that's my half-lives. Let me move back. So those are those sort of answers to those questions. How would the initial amount affect how easy it is to measure? And also how the different half-lives could help us out. Okay, don't worry about the assumptions for now. So let's move on to the atmosphere, okay? Because we've talked about the geosphere, which is that solid Earth part, and now I want to talk about the atmosphere, which is the mixture of gases that surround the Earth. And I think there's a really nice sort of obvious link into this, because we've just been talking about volcanic activity and things like weathering, and we want to be able to talk now about the atmosphere. So our atmosphere is that mixture of gases, so nitrogen, oxygen, argon, and then smaller percentages like carbon dioxide, water vapor, and that surrounds the Earth. So this is our atmosphere. So if you've ever wondered what the difference between atmosphere and air is, this is what it is. So the atmosphere is the gaseous envelope that surrounds a planet or other celestial body. So in other words, Mars has an atmosphere. Venus has an atmosphere. Okay? Air is the mixture of gases and particles that surround Earth. So Earth has air. Mars and Venus don't have air. They have atmospheres. Okay? So why is atmospheric composition important? So someone told me the answer just before, right? You said that things like the atmospheric composition will affect how warm our planetary temperature is because of the greenhouse effect. Why else do we care what the air is composed of? We breathe it. We like to breathe. And so it's important for us that the air is breathable. Not just that there's oxygen in it, but also we live in LA. And what do you usually see if you look at the atmosphere to the north of us? Smog. It's pretty nasty, right? So we care about the composition of the atmosphere also because it affects our health. What is it that's up in the atmosphere that also helps life exist on Earth? Ozone, absolutely, and we're going to talk about ozone much later in the class, as UCI has had a very important role in ozone. And so, yeah, all of these things are important. So some of these are connections that you might want to make on your concept map. So things like the greenhouse effect affects our surface temperature. But also, the composition of the atmosphere affects what weathering processes happen. It's what we breathe. It affects what type of biological activity you can have on Earth. It has ozone, which helps by sort of stopping that ultraviolet light coming through and damaging our cells. So these are just a handful of the reasons why atmospheric composition is important to us. So I said that we had both gases, but also some particles that make up our air. These are called aerosols, and everyone's familiar with that sort of idea of aerosols, but perhaps you might not know what they actually are. So aerosols are really, really tiny droplets, or tiny solid particles, and they're so small that they just stay in the air. Okay, so when we have those really misty mornings, we have the June gloom and things like that, then often it's really misty and you can waft your hand and you can see little droplets moving, but they don't fall out because they're light enough that that movement of the air can keep them suspended in the air. So here are some examples of aerosols. So things like smoke from our forest fires. Here you can see all of the aerosols produced by forest fires during one of the Santa Ana wind events. Things like ice crystals, sea salt crystals. So when you see that sea spray coming off the waves when it's really windy down at the beach, so a lot of that is ending up in the atmosphere. Dust, big dust storms coming off Sahara. Volcanic emissions, so things like ash. If it's small enough, it can stay in the atmosphere for a very long time. And then things like industrial pollution today, soot, nasty stuff that we don't necessarily want up there. And aerosols are complicated, and they're one of the things that we've had less certainty about in making predictions about future climate change. Because these things are important for our atmosphere because some types of aerosols will absorb incoming radiation. Okay? So some of them will act to heat the atmosphere. So for example, soot, like that black stuff that you can get from either fires or industrial activity, that will absorb incoming solar radiation and actually will heat up the Earth. But we also have a bunch of other types of aerosols, for example, things like sulfur, which act to reflect incoming radiation. So if we have enough of those in the atmosphere, then we actually start cooling down the Earth. Okay? And some are important for cloud formation because in order to get droplets to form, usually it's helpful to have something that they can form on. So you know that when a really cold morning, then there's dew on surfaces because it's easier for those droplets to condense out onto something. So some of these really tiny particles in the atmosphere are really important for cloud formation. Okay? So aerosols are complicated. And we're going to talk a little bit more about some of these as we get to examples. So, I know that you said none of you read the news, but hopefully some of these might be familiar images. So which of the following is an image related to a 2009 to 2011, I need to update this, a news story related to aerosols, okay? So you can talk to your neighbor and see if they can work out what all of these different things are. So think back, and what might these be related to? Okay, a few more seconds. Okay, I think everyone's had a chance to answer. So let's see how good your memory is. So D, all of the images, that is right, okay? And usually you can always tell this is the question, right? Okay, but does someone want to tell me, how about B? What do you think B is showing?
Icelandic volcano.
The Icelandic volcano, the one that I can't pronounce, the biogeochemical thing. And this was the pattern of ash. And remember, ash is volcanic ash is a type of aerosol. This was the ash in the upper atmosphere that stopped the planes flying across from the US to Europe and caused chaos for quite some time. Okay? What about C? Does anyone remember what C is? When was the last really big fire near LA? Do you remember the station fire? It's quite a long time ago now, but this was the station fire, and you can see this enormous amount of ash coming up from the station fire near LA. What do you think A might be related to? This is from 2011. What happened in 2011? It's the tsunami. And what in particular did the tsunami affect that we're still concerned about today? The nuclear power station. So in 2011, there suddenly started to be this scare that radioactive particles of iodine released from the Fukushima radioactive disaster after the tsunami could actually make their way across the Pacific and affect us here in California. And it was complete nonsense. They might have made its way over to us, but there's such little radioactivity associated with that that it really wouldn't make a difference. But this was something that people wanted to know about at the time. Okay, so we've done aerosols, so let's move on. And this is something that I mentioned very early on when we were talking about the formation of the Earth. So we had an atmosphere when Earth was very, very brand new. And it mainly consisted of hydrogen and helium. And because that was really the most abundant elements in our solar system, it's what makes up most of the sun, it's what makes up most of our big Jovian planets. But we didn't really keep it around for very long. First of all, because you all know, because you've been studying so hard, that hydrogen and helium is light. So do you remember when we talked about Earth being a mainly closed system? The reason it's mainly closed is because little bits of hydrogen and helium from our atmosphere are drifting off each year because they're too light to be retained by Earth's gravity. So that's the same thing that happened early in Earth's history. Our initial atmosphere of hydrogen and helium drifted off because we couldn't retain it with our gravity. Also, at that point, we still hadn't fully differentiated into different layers, so we didn't have a good magnetic field yet, and so we didn't have much protection from this solar wind of energetic particles. And lastly, of course, we have collisions. And the one that probably did sort of the most damage to that first atmosphere was the gigantic collision that formed the moon. And there's a couple of little videos there. One is the one I posted way back. The other one is like a Hollywoodized version with sort of looming, sort of dramatic music. But remember that something the size of Mars crashed into the early Earth just after it had sort of was forming. And so it remelted most of the mantle. And so you can imagine that any atmosphere we had then just got blasted off into space. So we ended up with this planet that didn't have an atmosphere. But we do today. So how did we get this blanket of gases and particles today? We got it from volcanoes, and we got it from comets. And I think that's really cool. If you look at the next glass of water that you sort of drink, half of that water came from volcanic eruptions putting out water vapor into the atmosphere, very, very early in Earth's history. The other half was delivered by comets, which are these icy bodies of gas and water crashing into Earth early in its history. Isn't that cool? I think that's very cool. And so our second atmosphere formed from these processes, from volcanic eruptions and from comets crashing into the Earth. And the main composition of the atmosphere at that time was carbon dioxide and water vapor. And that's because if we look at what volcanoes give out, then they mainly give out water vapor, carbon dioxide, and then smaller amounts of other stuff, things like sulfur gases, hydrogen gas, carbon monoxide, things like that. Doesn't really matter what different setting your igneous activity is happening at, those are the main gases that are released. So that was what created our second atmosphere. But we know that that's not what we have today, otherwise we'd be pretty dead. And so what we have instead is mainly nitrogen, oxygen, and a little bit of argon. And then some bunch of other stuff, things like carbon dioxide, methane, nitrous oxide, ozone. If you look at how much of a percentage of the atmosphere those are, they're a really tiny percent. But they are really important for how the Earth system functions. And then we have variable stuff, and the reason that this isn't included is because water vapor moves in and out of the atmosphere so quickly it's difficult to set a particular percentage. It's constantly changing, but it's not a huge component. Okay? So my question of the day is, why are we so different from Venus? They both had the same processes happening early in Earth history, but Venus today has this sort of really pretty nasty looking atmosphere, whereas today we have our beautiful sort of clear atmosphere. So why are these so different? Venus is Earth's evil twin. So what happened to atmospheric H2O? So what happened to all that water vapor that was erupted into the atmosphere from volcanoes? What happened to the atmospheric carbon dioxide? Where has it gone? We know that we only have a tiny percentage of the atmosphere today. Where did it all go? And where did the oxygen come from, which is my easy question of the day? Okay? So I'm going to give you 1 minute to talk with your neighbor and come up with ideas for each of these. So think about where you find H2O today. Think about where you find carbon today. Okay? Right, what do you think? Where is all my H2O? Where did all my H2O go? The oceans, I heard it yelled from over here. Yeah, absolutely. Where's the water today? It's in the oceans. Absolutely. So where did my H2O go? It's in the oceans. That atmosphere, our air, can only hold a certain amount of the water vapor that was erupted by volcanoes. So as soon as there was too much in there, it started condensing out, especially as Earth sort of cooled down a little very early on. And so it started condensing out, and over time it's built up to form the oceans, which are huge, obviously. And so you can see our oceans have over 97% of the water on Earth, and then some of it is in ice, and the rest of it, a tiny percentage actually, is in the fresh water that we like to use. And we'll talk more about that when we come to the hydrosphere. Okay? So our volcanoes, our geosphere, created not only our atmosphere, but also our oceans. Very important. What happened to the CO2? Where do we find carbon today? Sorry? Someone? Photosynthesis, I hear a comment over here. So yeah, absolutely, in the biosphere, we're made of, apart from a lot of water, we're made of carbon. Gigantic trees are made of carbon. All the sort of single cellular life around is made of carbon. So certainly some of the carbon has gone into the biosphere. Where else would you find carbon? In rocks, absolutely. And rocks are actually by far the most important one. So if we talk about carbonate rocks, sort of muds and things like that, shale, then they contain a lot of carbon. And so what we've done through time, through sort of the processes of weathering, through sort of biological activities, we've taken that carbon dioxide and we've put it somewhere else. Anywhere else? Does anyone else know what? The oceans, absolutely. That was my other big one that I wanted. So just like you can dissolve carbon dioxide in your soda, that's what the bubbles are made of in your soda, we also dissolve a lot of our carbon dioxide in the oceans. And actually, over half the carbon dioxide that we have put into the atmosphere by burning fossil fuels has actually ended up in the oceans so far. They've been saving us quite a lot from additional warming. Okay, so this is definitely the ones that I wanted. So carbon dioxide has been removed by the atmosphere, by the biosphere, by dissolution in the oceans, by chemical weathering. And that's that process where we dissolve carbon dioxide in water in the atmosphere, which makes our rain slightly acidic. And then that dissolves away different rocks or reacts with rocks. And over time, all of that carbon has been locked away in rocks and also as fossil fuels. And so you can see the different amounts of carbon in those different reservoirs, those different places today. Okay, and so I wanted to talk briefly about nitrogen and argon, because actually nitrogen is the most important gas in our atmosphere today. But if you look at, say, what the volcanoes were erupting, it wasn't on the list, and that's because the amount of nitrogen that's released by volcanoes is actually really, really tiny. The main reason that our atmosphere is mainly made up of nitrogen today is that it just doesn't react with anything. And so once it's in the atmosphere, it doesn't go anywhere. Okay? It's what we call chemically inert. So it doesn't necessarily react with anything on the Earth's surface. It doesn't dissolve terribly well in the oceans. And so whatever we put into the atmosphere, even if it's tiny amounts at a time from volcanoes, just builds up and builds up and builds up. And so our atmosphere today is mainly nitrogen. Okay? And similar things happen with argon, but argon actually isn't produced in huge quantities by volcanoes. Instead, argon is actually released into the atmosphere by radioactive decay within rocks. So one of the radioactive elements I talked about was potassium, and potassium will decay away into argon. Okay? And so just like nitrogen, however, even though it's being put into the atmosphere in very, very, very tiny amounts, once it's up there, it doesn't react with anything. It also doesn't dissolve particularly well, And so we end up with it building up in our atmosphere. Okay? And lastly, we want to talk about our third major gas. Where does oxygen come from? Plants, photosynthesis, absolutely. So the oxygen on Earth has actually built up through time after the evolution of life. For a very long time, over billions of years, the composition of Earth's atmosphere had hardly any oxygen in it. And it's really just in the last sort of billion years or so that we've started seeing significant percentages of the Earth's atmosphere being oxygen. And so photosynthesis started releasing this oxygen, and it built up over time, okay? And so since 550 million years ago, which is when all the interesting life stuff has been happening, which is probably tied into this because oxygen is easier to use in biological systems, our atmosphere has been between 15 and 35%. So what is it today? Does anyone know? Can anyone remember? About 20%. So actually we have had much higher concentrations of oxygen in our atmosphere in the past. And this isn't something that you need to remember, but associated with that really high oxygen content, we had giant bugs, okay? We had spiders that could eat your cat. We had dragonflies the size of large eagles zooming around. We had a giant millipede that could sort of rear up and look me in the eye. It was the length of a car, okay? Really crazy stuff. And there's a little cool video there about that time in Earth's history. Why do you think, though, that we've never had oxygen concentrations higher than 35%?
Oxygen's a poison.
It is a poison, but the Earth doesn't necessarily care about that. What would happen if I put you in a, yeah?
Because it's very reactive.
It's very reactive, absolutely. And if I put you in a room with lots of oxygen, and I got you to try and set fire to something, it might go bang, okay? And that's the thing, oxygen is really reactive, it burns very well, and so if we get oxygen concentrations much above that, then things like big fires, big forest fires could actually remove that sort of oxygen, so we've got an upper limit there. Okay, so listening to all that and what I told you earlier today, what do you think the most likely atmospheric composition of Venus is today? What do you think all those nasty looking clouds are actually composed of? A few more seconds. Okay, let's take a look. C, you would be right. C. Does anyone want to argue with me that it's D? Did anyone vote D and would like to argue? You would like to argue. We can argue later if you'd rather not do it in person. Okay. So one thing that hopefully I'm sure you're thinking is, well, hang on, you said that it was H2O and CO2 that was released by volcanoes, right? So where's the H2O? And actually, H2O is destroyed in Venus's atmosphere because it doesn't have a very good magnetic field and a couple of other reasons. So it actually creates sort of nasty sulfuric acid by reacting with sulfur gases instead. So C would be the right answer. It's mainly carbon dioxide, okay? Do you remember our 5 factors that we talked about that control planetary temperature? I'm sure you do because you've been studying hard. Then we talked about solar luminosity. We talked about distance from the sun, things like albedo and the greenhouse effect. Definitely Venus is closer to the sun than Earth, so you might expect it to be warmer. But if you take into account albedo, so how reflective those clouds are, then actually the surface of Venus should be cooler than the Earth. But because it has an atmosphere that's 96% CO2, it has just this gigantic greenhouse effect that actually means that if you were on the surface of Venus today, well, apart from being crushed, because there's a really thick atmosphere, then it would be way, way too hot. You would not be comfortable at sort of 400 degrees or so. It's really, really miserable, okay? And so, yeah, we've ended up with very, very different planets here because of the different sequences of information. Venus hasn't had this sort of plate tectonic activity necessarily, and it also hasn't had that evolution of life. So Earth's evil twin. Okay, so that's our atmosphere in the past. That's how we've evolved. But what about today? Today is sort of what we care about, right? And so we have our permanent gases. So these are the gases, the 3 gases that make up most of the atmosphere. So things like nitrogen, oxygen, and argon. Those are our 3 permanent gases. But we also have these variable gases as well that may make up less of the atmosphere, but they're actually most important perhaps for us. So things like water vapor are very important because it controls where and when we get rainfall and things like that. Carbon dioxide is having a very big effect on the magnitude of the greenhouse effect that we see today, along with methane, along with nitrous oxide. Ozone is a tiny percentage of the Earth's atmosphere, but it's obviously really important that it's up there so that we can actually live outside, and we did a good job at trying to get rid of that. Okay, so given what I just told you and remembering the formula for residence time, which is the residence time is equal to the amount in the reservoir divided by the sources or the sinks. Which of these gases do you think will have the longest residence time in the atmosphere? Okay, a few more seconds. Right. Nitrogen, and you would be right, because remember our formula. So our residence time is equal to the amount in the reservoir divided by the fluxes, the sources or the sinks. How much nitrogen is there in the atmosphere? A lot, okay? 70%, in fact, absolutely. And how much is going in and out each year? Very little. So we're dividing a big number by a really tiny number, and so we're going to get a really long residence time. Whereas water and methane, they have much shorter residence times because there's less in there to begin with, and also they have larger sources and sinks each year. Okay? So work through the math if that makes no sense to you. So if I look at our residence times, the nitrogen has a residence time of about 42 million years. And when we talk later in the course about the nitrogen cycle, we've actually had a huge effect on this number because of things like fertilizer production, but we'll come back to that. For water vapor, what do you think our residence time of water vapor is? Do you think minutes, days, years, decades? Days, absolutely. So about 10 days, that's how long the average water vapor molecule will stay in the atmosphere. And methane is a little bit longer, 10 years. If we look at CO2, it's more like maybe 100. So all of these variable gases have much shorter residence times. It's easier for us to change the amount that's in there. So water vapor, it's actually one of our most important variable gases for obvious reasons. We need water, we need fresh water in the form of rain and everything else. And so here is a brief overview of the hydrologic cycle, and I'm not going to insult your intelligence by going through it too much, but obviously we get evaporation putting water vapor into the atmosphere, and then condensation and precipitation and rainfall as removal, as sinks from our atmosphere. And obviously where it's warmer, we tend to get more water vapor, for reasons we'll come into next week. So at the poles, there's less in the atmosphere, and at the tropics, there's more. And this is, remember, our most important greenhouse gas. Water vapor is really important for the greenhouse effect on Earth. Okay. But I want to give you a word of warning. When I say water vapor, I mean the water vapor that's in this room right now that's an invisible gas. Clouds are something that's different. Clouds are actually liquid droplets or ice particles of water. Okay, so water vapor is the invisible stuff. Okay? Clouds are the sort of the condensed or solidified water in the atmosphere. So how much time have I got? Oh, I've got plenty of time. So let's talk about CO2. Anyone that's taken a class with me before should be fed up of seeing this graph by now. It's what we call the Keeling Curve, and this was started by a scientist called Keeling down from San Diego way back in the 1960s. And he very meticulously started measuring the amount of carbon dioxide we'd had in our atmosphere. And this was something pretty new back then. It's like, well, why do we care? But he could see how things were going, and he could see that we might start to have an effect on our atmosphere. And this is the most amazing time series of scientific measurements, and it's one of the most important ones we have. And last year, this sort of needs updating because we actually briefly went over the 400 parts per million. That's what ppm stands for, parts per million in our atmosphere. Okay? So that diagram I showed you on the previous page of what percentage our CO2 is now out of date, because we've got much more. And you can see that gradually it's going up. Why do you think it's going up? Because we're burning fossil fuels and putting carbon into the atmosphere. We'll come back to this in much more detail towards the end. But why do you think there are these wiggles? What are the wiggles doing? Yeah, they're seasons. You can see that every year it goes up and down. And the reason for this is to do with the biosphere. Because not so much here in Southern California, but definitely further north right now, what would be happening to the trees and things like that? Yeah, they'll be dropping their leaves. Things start to die off in the winter. And if we look at where most of the land is on Earth, the vast majority of land is actually in the northern hemisphere, rather than the southern hemisphere. And so what we see with those wiggles up and down is actually the response of the biosphere. So in winter and fall, things are dying, so there's more respiration, there's more carbon dioxide being returned to the atmosphere, the decay of that vegetation. In the spring and summer, then our vegetation is growing like crazy, it's photosynthesizing, and it's taking in carbon dioxide. And so I think this is really amazing that you can actually see this seasonal cycle in the CO2 of the atmosphere to do with the biosphere. And you can see that the size of that cycle is nothing compared to what actually we've been doing over the last sort of 30, 40, 50 years. Okay? So this is the Keeling Curve, and we'll come back to this again later in the class, so don't worry about those. So here is my little summary. We have our wiggles that are our annual seasons. Overall, it's increasing. Our sources are things like respiration, volcanic activity, anthropogenic combustion, so fossil fuel burning. And our sinks are things like photosynthesis, dissolving in the sea. Okay, so skip that. We'll come back to this later on Monday. Okay.